now. So welcome, good morning from Crete, from Heraklion, from the Hellenic Mediterranean University. First of all, I would like to thank the attendees for your participation, and I will appreciate even more your interaction with Eugene during the Q&A session. It's a great pleasure to have with us Professor Eugene Katz. He's like, according to my standards, a scientist, regarding his culture and regarding his involvement and his research and teaching. Professor Eugene Katz is a professor in the Ben Gurion University of the Negev in Israel. He obtained his PhD in 1990s from Moscow Institute for Steel and Alloys, back then the ex-Soviet Union. And his research interest involves photovoltaic characterization of various solar cells, organic and nanostructured solar cells, photovoltaic operation under concentrated sunlight. Regarding the latter activity, Ben Gurion and his laboratory is famous for this. This is the main innovation, among others, of the laboratory in Israel and in Negev. So, Eugene, as I mentioned to my email, it's a great pleasure for us. It's a great honor for my university to have among you. I remember when I first met Eugene, I was with Kakavelakis, probably Manolis Kimakis now, one of his most successful PhD students that Professor Kimakis' group has got. And we were waiting in Bratislava, and we were looking all the students, they were going to Eugene. I didn't know Eugene who was. And I was asking Kakavelakis, why all the students are going to this guy? We should learn who is he. So now now we know each other. So thank you, Eugene, to be with us, and please share your screen to start your presentation. Thank you.
Thank you very much, Kostas, for so kind introduction. Thank you very much. I hope you can see my screen.
Yes, we can see the screen. Thank you.
Can you see my screen?
Yes, sir.
Yes, you can see our campus. This is a photo of our campus in the middle of the nowhere, or in the middle of the Negev desert. And yes, I will talk today. If you can see these two icons, one is the Leonardo drawing of a truncated icosahedron like C60 molecule, and another one is a drawing Sun by Dürer. And during my talk, you will understand why I choose these two artists for artistic representation. And these two arrows shows our activity with this, because we try to use fullerenes for organic solar cells to use solar energy, and also try to use solar energy in order to synthesize fullerenes, more specifically inorganic fullerenes. But today I will almost not talk about my scientific activity. My talk about it's my hobby. It's mostly, it will be a history of science, and I will also talk about the structures, I mean the shape of the fullerenes from simple mathematical consideration, and we'll talk about these structures in molecules and nanoclusters, and also in microorganisms and viruses, and also in macro worlds, means in architecture. Yes, I will start with the story of the discovery of C60, and then try to explain something about Buckminster Fuller, who's a very unusual person, great personality. I also will talk about because it's a polyhedral molecules and structure, about a long history of mathematical exploration of polyhedra, but also in something about art. And finally, I will talk about Leonhard Euler's theorem about polyhedra. And hopefully, I will finish with explanations that all Fullerene-like structures of molecules and nanocrystals, viruses, microorganisms, and buildings may be understood by the same principles. Yes, just for many, many years, for a long time, we all know only two allotropes of carbon, is graphite and diamond, with completely different properties, opposite properties. But in 1985, this was broken by discovery of this molecule C60. To understand it, we should think about the graphite structure, which is van der Waals connection of planes. We call graphenids today, and Manos, the Mr. Graphene is wow, sorry. I didn't say that. Thank you very much, Kostas and all organizers, for inviting me. I'm very happy to be in Crete, just virtually, but hope to come sometime in reality. Yeah, yes, yeah. About graphite, this is a very unusual crystal, which very strong anisotropy. Why? Because in this direction, it's a very small forces, van der Waals forces, but it's a covalent bonding in a graphene plane with hexagonal packing, with close packing of hexagons. Yes, and we can start our story of Fullerene science, modern Fullerene science, long before the experimental discovery of C60. You remember, it's 1985, when David Jones published his suggestion. David Jones, he's not a scientist. He's a very unusual personality. Every week, he published some suggestion, scientific conjecture, first in the journal New Scientist and then in Nature. Under pseudonym Didalos, it's good to say in Greek. It will be some, I will also talk about Archimedes and Plato, and it's good to do in Greece. And what he say is he suggested that implanting of pentagonal defects into hexagonal graphene layer might transform this flat layer into a giant closed cage molecule of carbon. He also point out that it should be 12 pentagons, and we will mathematically prove today that it should be no less and no more, 12 pentagons. It's interesting. His ideas, couple of his ideas got the Nobel Prize. Also, other guys got the Nobel Prize, the scientists got the Nobel Prize. Some of these ideas may be not realized, but it's very, very unusual, and we should give him a credit. 1966. Then in 1970, Eiji Azawa, he's still alive. He's a great person. I really was happy to communicate with him a number of times. Published a paper in Japanese with a structure which he called Fullerene. Let me check if I can do options. Yes, pen. Can I do it? Okay, 1 second, one more. Go pointer options, ink color. Yeah. This Fullerene, and he believes that this is aromatic structure. Today we understand it's not exactly correct, but he really theoretically talk about C60. Later, Eiji Azawa translated all his papers from Japanese to English with only one example, this paper, because he believes that this paper is not important. And then 3 years after, 2 Russian guys, also in a strange language, means Russian, published already quantum chemistry calculations of electronic structure of C60, showing that there is a big distance between energetic gap between HOMA and LUMA, means that this structure must be stable. And the author of these papers is a great Russian scientist, Dmitry Bachwar. He's great in both mathematics and chemistry. And Elena Galperny. Elena is still alive, and I'm in contact with her for a long time. But it was another author of this paper. It was Ivan Stankiewicz. He's died already, but he was a really very great personality, and be very, very honest. He suggested to calculate C60 because they started with first carbon 20 and then realized that it's not stable. But he asked to delete his name from the list of first paper. Now, after all next papers, he was one of the authors. He was very active in theory. But even more, it was an experimental paper 1 year before the discovery of carbon 60, and it was one of the postdocs, former student of Smalley, who was one of the discovery of carbon 60 and Nobel Prize winner later. What they measure mass spectrum. You can see this mass spectrum of carbon clusters, as a function of number of carbon atoms. And you can see first these small clusters, which was very known a long time, then some gap, forbidden band gap, and then status from carbon 66. Now we understand all these are fullerenes. This is a fullerene members. And the most stable and abundant molecule is carbon 60 and carbon 70. All these clusters has even number of carbons, and I will mathematically prove why it's even number of carbons, but 1 year before, nobody put attention on that paper. So then we come into 1985, British astrochemist Harold Krotter was very active in astrochemistry and spectroscopy for astrochemistry for that time. And actually, he was interested in carbon-rich stars and in carbon clusters. And his idea was to reproduce in a laboratory some spectra and compare it with the reading from the space. And then he come to Richard Smalley, who was active in cluster science and can produce clusters of semiconductor and metals. And also he told him, we can also do it for carbon. Actually, this photo I made in Jerusalem 1 year before the Nobel Prize for physics discovery. It was a conference on fullerenes in Jerusalem. And after that, it was a dinner in an ancient Roman restaurant. So everyone got this, not only the first Nobel Prize winner, Richard Smalley, everyone gets this flower. Yes, this is a schematic of the experiment. Yes, Smalley told Krotter that he can come, but the lab is very busy, and he can give him students to work, but they can work only during nights. And during 6 nights, they did this experiment. The experiment is the following. The laser light vaporized rotating graphite disks in vacuum, and then it was a ultrasonic injection of cold helium for clusterization, and then cluster go to mass spectrum. And one night they found a very strange spectrum. They found that there is a predominance of cluster with 60 atoms of carbon, nothing else, just carbon, and there is another also signal with 70. It means that under these conditions, there is a formation of stable molecules of 60 atoms of carbon, which people didn't realize before. So it was a big discussion between them. Should they also suggested a structure or not? Because when you do mass spectrometry, you have no any information about structures. For structure, you need to do nuclear magnetic resonance or some kind of other method, but you need a mass gram, mass quantity of the material. But nevertheless, they suggested a structure, and this structure of what was the requirement for the structure? The molecule should consist only on carbon atoms, and all 4 valence of carbon should be satisfied. Only 60 carbon atoms. So what they suggest is a structure of a polyhedron, so-called truncated icosahedron, with 12 pentagons and 20 hexagonal faces, and 60 vertices, and every vertex is in equivalent position. It's carbon atoms, but there are 2 kind of ages. There are 2 kind of chemical bonds. One is the age between hexagon and hexagon, is double bond, and another one is a single bond, is the age between hexagon and pentagon. Yeah, and they submitted a paper to Nature, and it was just a speculation, but the paper was accepted. And it was 1985 again, 5 years after, 1990. the German-American group, suggested a method how to produce C60 in mass quantities, and everyone started to do it. And 1996, Krotter, Körl, and Smalley got a Nobel Prize for the discovery because this idea was completely proved, and the diameter of molecule was measured, the length of bonds, etc., etc. So I would like to say two words about symmetry. In a Nobel Prize lecture, Krotter says that the story of symmetry cannot be recounted without reference to its beauty. Before that, let's talk about symmetry before, which results from its incredible symmetry. This is a pentagonal group of symmetry with even five-fold symmetry, which was for that time, it was just before discovery by Danny Shechtman of quasicrystals. So there was no way of such symmetry in crystallography. But even if you read the books of Landau and Lifshitz, which let's say some kind of Bible for physicists all over the world, in addition, it was written in 1948, and we can read that these groups, this is icosahedron group of symmetry I and IH, are no physical interest since they have not realized themselves as symmetry groups of molecules. And now we know that it's a lot of molecules with this symmetry, and symmetry, of course, it's very important for understanding of properties of fullerenes and whatever. And then Krotter continues, another important aspect of the molecule aura lies in the name Buckminster Fullerene and the direct association with the geodesic domes designed by Buckminster Fuller. It invests this elegant molecule with a charisma that has fascinated scientists, delighted lay people, and has infected children with a new enthusiasm for science. But what is it was a big discussion about this name. It was suggested by Krotter, and C60 they call it Buckminster Fullerene. And some people say it's too long, and some people say nobody knows who is Buckminster Fuller. And Krotter, he was a big fan of Buckminster Fuller. He say, but now people will learn it because of our molecule. But who is Buckminster Fuller? And it's very interesting. If you look I wrote it from Encyclopedia Britannica, but you can read the same in Wikipedia. He was an architect, philosopher, engineer, inventor, author, cartographer, geometrian, futurist, teacher, and poet, and one of the most original thinkers of the second half of 20th century. He died actually 2 years before discovery of C60. In 1927, he formulated the aim of his life. He was unemployed on this time. But I didn't say, but Ozawa also was a long time unemployed after his postdocs. And Krotter also was almost unemployed. His aim was at a non-profit search for design patterns that could maximize the social uses of the world energy and industrial resources. What does it mean? That he wants to build something more efficient, more simple, and more cheaper with less materials, whatever, and build it on the basic of mathematics, of main design principles. So he built his first calls. He also want to play with words. He invented words dimaxion. The dimaxion was dynamic maximum. He suggested his first dynamic maximum building in Texas in 1922. Not suggested, build it. And he still exists after a number of earthquakes with many buildings was killed. It was also energy is the solar energy, and it's you see the round. And he also want to build and actually build, but he didn't get a name of Dymaxion car. That the aim was that this car will also use an airplane. But even in 1933, he got 190 kilometers for 12 passengers. It's really very, very interesting results. Then he formulated his ideas on the most important language for this language of mathematics. And he says the following, that we all live in our own architecture. We all live in cubic architecture. Look on your rooms, at least on my room, let's say. We all live in cubes. And squares in cubes is the most unstable structure in the world. What is the most stable structure in the world is triangle or tetrahedra. He got a lot of credit for tetrahedral structure of in his lectures, or of carbon structure, sp3 carbon bonds. And if you want to produce something stable from these structures, what you need to do, you need to enforce it by create triangles inside, either triangle or tetrahedron. And he say, if the tetrahedral geometry is more stable, why we use this Cartesian coordinates? Let's use the tetrahedral coordinates. And he suggested it to mathematicians. Okay, mathematicians didn't like them, but he said, okay, I will prove that it's true. And all his inventions was, his personal aim was to prove that his mathematics is correct. His system coordinate is correct. But anyway, in 1954, yeah.
Petro,
Just a moment, Eugene. Someone has forgotten his microphone, so okay. You can continue. Sorry about this.
No. But anyway, if you want to ask question, feel free to interrupt me, and let's do it. And in 1954, he got the first patent for geodesic dome. Geodesic dome is, I will introduce the main principles, but this is a Fullerene-like architectures. He built a huge geodesic dome in the United States in 1958, and and continues. And you see one of them. And today you can see this, the most famous maybe his building is this US pavilion for World Expo 67 in Montreal. You can still even visit it. It's a museum of ecology or something like this. Just because of I see one of my Russian colleagues in the audience, that I'd like to say that he also built in Moscow the building for the first American exhibition in 1958, I think. It was the real very first American exhibition. It was a very big political event. It was a couple of years after Stalin's death. Some principles of geodesic dome. The geodesic sphere is a polyhedral structure could be effectively inscribed in a sphere. Geodesic dome is just a fraction of the sphere, and it can vary from 5 to 10%. A sphere is already efficient. It encloses the most volume with the least surface. Any dome that is a portion of a sphere has the least surface through which to lose heat or intercept potentially damaging winds. A geodesic dome uses a pattern of self-bracing triangles. It means that if you have a geodesic dome built by pentagon and hexagon, every pentagon should be divided by 5 triangles, and every hexagon should be divided by 3 triangles. That gives maximum strength and stability using the least material possible. He introduced a parameter frequency of a dome that relates to the number of smaller triangles into which it is subdivided. A high frequency dome has more triangular components and it's more smoothly curved and sphere-like. And then he says that, and it's true, the geodesic domes get stronger, lighter, and cheaper per unit volume as their frequency and size increases. Just the opposite to conventional buildings. Yes, today we all have a problem with Fullerene-like virus, COVID-19, and this is, but what is interesting, when these spherical viruses, which also has these structures, was discovered, the first paper was published by Donald Kaspar and Aaron Klug. In the paper, they get in acknowledgement, they get a respect and thanks to Fuller, saying the following: the solution we have found was in fact inspired by the geometrical principles applied by Buckminster Fuller in the construction of geodesic domes, and his physically oriented geometry of efficient design. But in his Nobel lecture, Smalley mentioned Archimedes as the first researcher of truncated icosahedron. Why? Because the C60 shaped truncated icosahedron as a modern soccer ball is one of the 13 so-called Archimedean polyhedra. What is this? This is a semi-regular polyhedra, which all faces are regular polygons, and all, C60 or truncated icosahedron is number 4, this one. But all vertices in an equivalent position, in a symmetrical position. But why are semi-regular? Because they have two kinds, like pentagon and hexagons, or maybe even 3 kinds of different polygons as faces. And what is interesting is that the manuscript, Archimedes manuscript, was lost. And in Europe, the mathematician didn't know about it, contrary to the Persian and Arab mathematician. And all these polyhedron were rediscovered in Renaissance time by great mathematicians. Most of them were also great artists. I will mention them. And then you see the original structure from Johannes Kepler book, The Harmony of the World, where he already formulated that this is 13 polyhedra and mathematically proved. So, because it's only, not only, but it's allowed 2 kind of faces, that's why they differ from regular polyhedra or Platonic polyhedra. And all of you, of course, know them. It's only 5: tetrahedron, cube, octahedron, icosahedron, and dodecahedron. We call it Platonic, but they were probably discovered even in a Pythagoras time. And we all know all of them in nature, and cube and octahedron mostly in crystals, but some forbidden chemical compound like cuban, for example, they were synthesized in 1964. You can see this is a quasi-octahedron. This is my photo in Louvre in Paris. Actually, it's just a pyramid, but because of reflection, it became octahedron. Yes, what is most interesting for us is dodecahedron and icosahedron with symmetry of C60. Again, it's forbidden in crystals, but it was found in quasi-crystals after the first discovery by Danny Shechtman. But what's interesting then, I found, this is my photo of period. This is iron sulfide in Natural History Museum in Washington, D.C. And I know that it's not, of course, a 5-fold symmetry. Why? Because the edges are not equal. And I measured it and proved it. Yeah, it's not. It's just a cubic structure. Yes, you can also find a lot of in art and icosahedrons, but look on this table. This table will understand us to understand something. This is the parameters of Platonic hedrons, number of edges which meet in each face, edges that connect in each vertex, number of faces, number of edges, number of vertices, and some magic number f, number of faces minus number of edges plus number of vertices, which all equal to, for any of these Platonic polyhedra, but we will learn a bit a couple of minutes later that it's for all kind of polyhedra like sphere, not only for Platonic. But look here, if you think about cube and octahedron, and you think this number, this is 4, 3, 3, 4. It's just anti-symmetry. Then 6, 8, 8, 6. Yeah, and the same with octahedron and dodecahedron. It's the same symmetry, and the mathematicians say that this polyhedra are dual. The cube and octahedral are dual to each other. The same icosahedron and dodecahedron, but tetrahedron is dual to itself. Then we can also use in this table, we can understand what's happened, how we can produce Archimedean truncated icosahedron from Platonic icosahedron. We will just cut the polyhedron near to every edge, near to every vertex. How many vertices come to icosahedron? In every vertex, 5. So we will produce pentagons. How many? It's 12 vertices for icosahedron, so we will produce 12 pentagons. So we will have new polyhedron with 12 pentagons and 20 hexagons instead of what we have in icosahedron. Most of polyhedron books gave the credit to the Leonardo drawing for truncated icosahedron. He didn't invent it, and he did this drawing for the book of his friend Luca Pacioli. I will show his portrait. He was a monk and mathematician, close friend of Leonardo. But what Leonardo invented, he invented the way we today call it method of solid edges, how to draw this. And everyone after Leonardo started to use it. Yes, and he drew it in every about 50 illustrations for this book in both methods, method of solid edges and method of solid faces. And if you look, for example, on C60, you just draw edges by lines like we can do. It's just a mess and so beautiful you can understand what it is after Leonardo. Yes, then you can see this is I told you that all these Archimedean solids were rediscovered, and Luca Pacioli rediscovered this rhombohedron, and this is his portrait done by Italian artist Jacopo de Barbari. And Luca Pacioli look on his invention of this polyhedron. Luca Pacioli, we know it was a number of his portraits, we know how it looked like, but today still historians argue about his personality because, and I'm among those who blame him for the plagiat of his teacher. His math teacher was a great artist, Pier della Francesca, who was a rediscoverer of truncated icosahedron in Europe. And Luca Pacioli in his book just copy and paste without giving a credit. Other interesting question, who is this guy near to Luca Pacioli? And some historians of art say that this is Dürer, Albrecht Durer. We don't know it for sure, but what we know for sure, but Albrecht Durer also made a great deal with polyhedral geometry, and he was the first who suggested to produce solid nets. And all people today in chemistry or crystallography use these solid nets if you want to build 3D. And you can see his solid nets from his book, his manuscript for dodecahedron and truncated icosahedron. Today, we know that if you want to produce truncated icosahedron, you see in a Dürer net, it's a hexagon and pentagon. But we know today that we don't need pentagon. If we just start to make a buckyball from the net only built from hexagons, the pentagons will be produced simultaneously, just like holes in this structure. So this may be how the nature built it by this hexagons, which you can get it from graphite structure and from chemistry. Yeah, this is what we call today Dürer solid. He's a very famous art which is called Melancholia 1. Yes, this is Pier della Francesca first manuscript. This is in Vatican Library today. He was a guy who was the first draw in Europe truncated icosahedron. Actually, I walked in Vatican Library with this manuscript, and I will tell you, it's really true. And and as I told you, Kepler finished to do it. But then, at the middle of 18th century, Leonhard Euler, he was in Russia for that time, in St. Petersburg. He suggested for any convex polyhedra, if you remember this table, number of faces minus number of edges plus number of vertices is equal to 2. I would like to say that something before that, 1 century before, it was some theorem was suggested by Descartes, but also his manuscript was lost, and it's like a detective story. If somebody is interested in this, I can answer on the questions about this, but he couldn't finish this because Euler was a guy who introduced an idea of edges. Descartes only talk about faces and also angles, vertices. Anyway, today we know the general Euler theorem for other structures, like not convex polyhedra will and maybe not equal to 2, and we call it Euler characteristic. But let's think about Fullerene structure. How we can use this formula to produce entire, not only C60, but entire Fullerene structure, and to explain why C60 and C70 is more stable. Let me give a definition for the moment, that fullerenes are close cage molecules of pure carbon in the shape of polyhedra with only pentagonal and hexagonal faces. If it's true, the number of faces will be equal to P plus H, where P is number of pentagons and H is number of hexagons. Because two edges come together, two faces come together in one edge, double number of edges is equal to 5P plus 6H. And by the same logic, because three edges come to one vertex, triple number of vertices is also 5P plus 6H. Let's now do very simple arithmetics, and I multiply this by 6, this by 3, and this by 2, and take this minus this plus this, and I will immediately get that 5 minus E plus V will be equal to P, but this is equal to 2, according to Euler. What does it mean? It means for any structure, doesn't depend on size. It can be building, can be molecule. It doesn't depend if it's regular or not, but if it consists only on pentagon and hexagons, the number of pentagons should be equal to 12. For me, it's an amazing result. But we can vary number of hexagons, and you will see it, that in now we can derive all structure. The minimum Fullerene and could be dodecahedron, carbon 20, with only 12 pentagons, nothing else. Then we add hexagons, and we immediately come to all number of vertices for all the structure will be even, if you remember this. So for some mathematical reason, again, no physics, no chemistry, just topology, H equal to 1 is forbidden. Carbon 22 doesn't exist. But then you get carbon 26, carbon 24, 26, sometimes 60, 70, and go whatever. So if you remember this figure I showed you before, all these numbers are even number, and we understand that all of them are fullerenes. But now, why C60 is more abundant and more close? It's by two reasons. C60 is a minimum fullerenes which satisfy to so-called isolated pentagon rules. What does it mean? That chemistry doesn't like pentagons, and C60 is the smallest fullerene where there is no any border between two pentagons. Every pentagon is surrounded by a ring of 5 hexagons. And the second reason that this is a more abundant is symmetry. Chemistry does like symmetry very much. So the next one, there is a fullerene between C60 and C75, but no one satisfied. And the next molecule, which has at least one satisfying to isolated pentagon rules, is carbon 70. That's why C70 is the next fullerene. And yes, I'm talking about the symmetry. Then if you produce C60 and cut it by 2 halves and add the 10 additional atoms, you can get C70. If you do it 2 times, and some people call C70 today rugby balls, like we call buckyball or whatever, football end. Yeah, if you do it 2 times, you got one of the isomers of carbon 80. But what's happened if you do it infinite number of times? You will produce a closed carbon nanotube. And the carbon nanotube is, of course, if it's closed, it's a member of Fullerene families, satisfied to all the requirements, is with six pentagons on one end and 6 pentagon another one, and only, and you can produce it by different way. You can just take a piece of graphene and scroll it all in the cylinder, and then 2/2 of fullerenes. And yes, after we now know that this is a Gima paper, famous paper about multi-wall nanotubes, and today all kinds of. Some time ago, I read a paper by Manos Koumakis, and it's a good idea to add carbon nanotubes to organic photovoltaics instead of C60. And with a couple of students, we spent some time to study this. So that's when I met. Then after many years, I met Manos after this first reading. But he was, I think, in Cambridge that time. Yes, when the paper was published. Yeah. Now, Buckminster Fuller nanotubes paper. But my favorite nanotubes building was built before, strongly before Fuller, by a great Russian architect in Moscow. You can see, and even now, even enter to this building. This is his own building in center of Moscow. His name is Konstantin Melnikov, and this is completely nanotube structure. And when I visited this building first time, strongly before it is a museum, becomes a museum, and I talked to Konstantin Melnikov's son. Now he's also an artist. Now he died already. And I told him that this structure is the most stable structure in the nature. For that time, we didn't know about graphene stability, and didn't know about graphene. And he told, yeah, it's true, because during the Second World War, the bomb came to the Vakhtangov series, a building very near to this building, and all buildings around was destroyed or just has cracks. And in our building, we only lost all windows, but it stayed. Yes, now if you produce a giant fullerenes with icosahedral symmetry, you will see that you will do flat, because of this Euler requirement of 12 pentagons, you will get more and more flat. I will, maybe because of time restriction, I will miss this long citation, but anyone can read it when I send a PDF to Kostas. So, yes, Ijima found the carbon onions, and today we onions, this is a multi-wall fullerenes. And again, the first is C60, this one, but if you look on the big outer shells, you can see they are more polyhedron than spherical. Yes, with my dear colleagues, Eugene from Taiwan, we published a very nice paper about the structure, these structures of Fullerene and Fullerene duals in a Chinese culture. Also some mathematics. All these structures are wrong, because these great Chinese artists didn't produce the entire ball. So if you take this, start to analyze it, you can understand this is a wrong fullerenes. But it's really, look on the time. It's forbidden. These photos, it's from Forbidden City in Beijing. Yes, most of architecture and viruses has a Fullerene duals rather than Fullerene structures. Yeah. Now, if you want to produce Fullerene-like structure with a negative curvature, and nature built it nicely today, you just add a heptagon instead of pentagon and hexagons. No, not instead, in addition, and get this. All the structure now are experimentally proved. So if you take a graphene sheet and add one cone, one pentagon, you get carbon nanocone. And if you get more and more, up to 5, you will decrease this angle. And what's happening if you get this nanohorns is a real structure with 5 pentagons, and this is the experimental figure, and they also use it in OPV, organic photovoltaics. But what happens if you add 6? You can get carbon nanotube. Yes, is it possible to build fullerenes from other elements, non-carbon or inorganic fullerenes? Yes, it's possible. And Israeli chemist Reshev Tener first suggested and then experimentally proved that if you have a inorganic crystal with structure similar to graphite, you can produce nanotubes and fullerene-like structure from these materials. They did it first from molybdenum sulfide and tungsten sulfide, and you can see Reshev beautiful macroscopic structures. But the only difference with carbon is that there is no C60 analogies, and there is almost no. I will show you one photograph of our photograph of single wall nanotube from molybdenum sulfide. Almost no, all of structures are multivolt. Yes, we work with Reshev for many years together because we want to produce, he wants to produce this structure not by laser ablation, but sunlight ablation. We concentrate our sun, we can concentrate under huge, under 10,000, 15,000 suns. And this was, I told you, we produced the first image of single wall molybdenum sulfide nanotubes. And also by laser ablation, Reshev many years couldn't produce. It's called cesium oxide fullerenes because it's a very reactive material, unstable in a nanoform, but in a fullerene form. Yeah, it's possible. Yeah, this was our work in this. Now, fullerene-like structure is animate nature. We already talked about viruses, but still there is a discussion. Could viruses be considered as living organisms? Some people say yes, because they have genetic materials, DNA, RNA, and can reproduce themselves. Some people say no, they have no cell structure. Yeah, they also know why they can reproduce themselves, but they need us to live with us to do it. This is some hope for that this COVID-19 will not kill all of us because they really need us. And but what we can say for sure, these viruses are on the very boundary between animate and abiotic nature. And this is very important because it seems that nature, evolution, was building structures with decrease of symmetry. More complicated organism has less and less symmetry. And just also want to show this beautiful creation, bacteriophages. Yes, it's bacteria who kill viruses. Yes, else you should enjoy. Everything is translation from Greek. Yeah, so this is a pentagon, or I would say fullerene-like structure where they have their DNA. Then they have something like nanotube which connects to the huge bacteria and insects their DNA on this bacteria. And starting from this moment, the bacteria start to reproduce bacteriophages instead to reproduce themselves. This is one of the fantastic inventions of nature. Yes, Radiolaria. This is the simplest organisms which live in oceans, in the sea and oceans, and produce skeleton, fullerene-like skeleton from water, from actually salt of silicon salts, but they produce it from the water by themselves. And you know that if you produce something by yourself, you need to have the same idea like Fuller and to do some stable and cheap. Yes, and this is a beautiful figures of this. It's actually, this is a famous drawing by Herkel. But the mathematics we use today, which I just demonstrate you, we got it from them. In carbon science, David Jones, who published the fantasies every week, was the first who did it and who showed that we really need 15 pentagons. Then Eugene also published it in his paper in 1980, and then Crotta and co-authors all in Fullerene science. But all of them gave credit to the book, which is called On Growth and Form, when Darcy Thompson published this mathematics for analysis of radiolaria. So we can say that we got it from this scientific relay race, Darcy Thompson, Jones, Eugene, and Crotta. And this is a very famous book, which was reproduced the first by Cambridge University Press. The first edition was published in 17, and then went doing many times. But what I found that, and I also published about it, that this kind of mathematics was done before in a first edition of Darcy Thompson book. You cannot find this mathematics, and we know today that he read the book of Russian mathematician Dmitry Mordechai Boltovskoy. He knows Russian. Darcy Thompson knows Russian, and both of them were also very strong in Greek and Latin. And Mordechai Boltovskoy was the first was the first translator and author of huge comments on Euclid elements in the Russian. And then this is his book when he published in 36. And in this paper in Mathematical Intelligence, I also give this credit to the great guy. He also was a very, and we now republish this paper, this book. It's called Geometry of Radiolaria, unfortunately only in Russian, but with my introduction to this. So I think I finish, and I think I have still some time maybe for a couple of questions, and thank you very much for your attention.
Thank you very much, Eugene. If you should please stop sharing the screen.
Yeah. Sure.
So
Yes.
thank you. Very inspiring. I mean, I'm very much impressed by the symmetry that nature hides. And all the secret is, according to your presentation, all the success is behind this kind of symmetries, because you mentioned Euler, Kepler, Archimedes, Kroto, of course, Tenek, Katz, even, Kimaki's work, it was based on this kind of symmetry. And I think that, from now and then I will look my wife and I'm thinking that I'm looking a pentagon or something like this. So it's impressive.
But Kostas, you must look on pentagon everywhere and hexagons, but we should know that the Fullerene family has a lot of fullerenes with no icosahedral symmetry. Just the only most abundant, most stable molecules
Exactly.
has this kind of symmetry, C60.
Exactly. I have a question on this, but first of all, I will give the floor to the attendees before I will make my question. The floor is yours. If you have any question, please switch on your microphone and start.
Could I ask a question, please?
Of course, George, of course.
First of all, I loved your talk. Wonderful stuff.
Thank you.
Let me just ask you, you mentioned that it's a combination of symmetry and topology. You had this argument, which I loved. What about energies? Should one not worry about lowest energy states? Because, or is it equivalent?
Yeah. Sure. We only, what I did by purpose, I talk only about simple mathematics. But as soon as you come to chemistry and physics, you start about symmetry. Yeah, when I say chemistry doesn't like pentagons, what does it mean? That it's a topological defects which introduced energy to the system. But why? It's a very good question. Then using this question, I can explain our view today, why fullerenes and carbon nanotubes are formed. Let's think that you have a graphite. Yeah, no problem, big crystal. And then you go to small nano structures, and graphene or whatever. And then you have a lot of dangling bonds. It's a very energetic defects. And nature preferred to introduce less energetic defects, pentagons, to build these closed structures. All this is about energy. Yeah. Or to build nanotube structure, whatever. Yeah, sure.
Wonderful, thank you.
We can see that. So we used to say that everything is physics, but it seems that everything is like mathematics now. Geometry, but
yeah, no, but we should not be. Albert Einstein told us it should be simple. as simple as possible, but not more. So it's very dangerous when you say nothing else is important. Yeah, okay.
May I ask a question following George Kavulakis?
Of course, Professor Christakis, the floor is yours.
Thank you very much. Before my question, I want to address to Professor Eugene Katz a very deep thank you, because he offered us an open mind view of the world through his own experiences. Not to be very fatal, I will follow George Kavulakis' question with a remark. I have worked on turbulence, and looking at the spectrum you have shown us with the ion signal, the ion signal spectrum, I remember this the turbulence spectra following a Russian mathematician and physicist, Kolmogorov, who offered a theory on turbulence, providing the possibility to see similar spectra. The fluid flow present a lot of examples. I don't want to take our time presenting all this experience from fluids, but Chandrasekhar and a lot of other researchers have provided similar to the ion signal spectrum pictures. Some other people have done work on nuclear physics.
Yes.
Seeing that a symmetry similar to the molecular symmetry exists also in the nuclear physics, nuclear scale of analyzing nature, because nature is nature. It is us who change scale from,
Exactly.
okay?
Exactly.
So seeing that cutting down the nature into pieces, we see that some laws are repeated. So this geometry does not explains and represents and analyzes and so on only in the scale of macro physics, in the scale that we see the world, or in cosmological scale, but also up to what we were able by means of laboratory means to observe. And one should think that can we state that under the nucleus pieces, the how they are called, those small pieces, the
Quarks.
quarks, yes.
I was contacted by quark physicists, and we talk about the same structures in quarks. And now it's a couple of publications, yes.
And do the quarks have their own structure? And
yes.
do the structure of the quarks have its own structure?
First of all, it's very dangerous to answer because I'm not real physicist in quark scale.
Yeah.
All my interest in solid state physics, but I was I don't know if we can say about real structure of quarks, I mean geometry of quarks, but they need some symmetry consideration for sure. It's now I was contacted very just couple of months already on the pandemic time by quark physicists talking about that. They sent me the paper about this kind of Fullerene-like model of quark geometry. Yeah, that's true. And I of course share everything what you say, that the nature organized something using the same principle on different levels of organization. Of course, it's not the same. We should analyze then the details, but the mathematical principles maybe the same. Yeah, I agree. And I also, maybe if you can send me the references for this, you say that after Kolmogorov, this kind of turbulence paper, I would really appreciate it if you send it.
Yeah, and it was a very historical paper because it was presented in Marseille in 1941 during the first months of the Second World War by Monin, a Russian meteorologist, and Kolmogorov. You can imagine the environment in Lyon at this time. One last word. Do you have imagined what happens with the structure of language? And if the structure of language has some symmetry?
I think that there is a symmetry, yes, and I know it because actually I'm a member of the society which is called Interdisciplinary Society of, International Society of Interdisciplinary Study of Symmetry. And one of the congresses was on Crete many years ago. And there are some linguists between us, yes, but of course, I couldn't comment.
Can we have your presentation?
Sure. Yep. I already Kostas asked me to send a PDF, and of course, I hope Kostas will put a presentation also on a YouTube channel. Yeah, sure. Yes. And Kostas has my email or whatever. Please be in touch about these references. Thank you very much.
Thank you very much.
Thank you. Thank you, Professor Christakis, for the question, and also Professor Katz for the replies. I think that if we don't have any other question, thank you, Anne. I don't know, Anne, what is we have also together with us the Vice Rector of the University of Orleans, a graduate, you have a PhD from Oxford or from Cambridge?
Cambridge. No.
So you have something in common with Professor Kimakis, because Professor Kimakis also was mentioned about his work in Cambridge in carbon nanotubes. Now we have another Cambridge PhD
but human and social sciences. So I need to.
But
I could have listened
everything is the same.
But
everything is the same.
There are no
borders between science.
I cut it in my talk. I cut it all art and.
I saw that absolutely.
Yeah. But I cut it from the lecture. Now I submit my proposal syllabus for the rector to make some kind of course on a Department of Art, but I don't know if it works or not. But it can be another story about this in Renaissance time. Why they do these great artists do this polyhedra geometry for us.
And actually, if I can cut in just with because I was, you had so many references to architecture. And I was sure that Oscar Niemeyer, the architect who did Brazilian, and who did because you had many pictures from Paris. There's also the headquarters of the Communist Party in Paris that he designed. And I was sure that he did some sort of structure like this, but I Googled it at the same time. I haven't found anything, but that's.
I think he didn't get Fuller-like geodesic domes. But he, of course, did many interesting architecture. In Israel, he built a university building of University of Haifa, not Technion. There is a second university in Haifa, and it's done by Niemeyer.
Okay, you have a beautiful campus, by the way.
Kostas will be with us, but Manos should come when this crazy time will finish. And everyone is welcome. If you're in Israel, please come. We are living in the most safe and international part of Israel. And we try to build it from scratch.
Yeah, I would like to talk to you as the Vice President of the new Research Institute of HMU. And we are honored that we have a scientist like you as a friend, as a collaborator. And we thank you very much. And now that after your talk, I'm now about 2 meters higher, that you mentioned compared with all these names. Okay, a little bit of modest. Thank you very much. And hopefully we will start a fruitful collaboration in many things after this COVID experience, and we'll definitely visit you. Also, we have some programs together in Erasmus, and we will apply for funding together as we are doing. Thank you very much, and it's a pleasure and honor that you came and gave us this excellent talk. Thank you.
Yeah.
Hello. I want to speak to Professor Eugene, if I can. I'm Manuel Markoulakis. I'm here, a PhD student in the university here. And Professor, we are very pleased to hosting you here in our university. And then thank you very much for this enlightening speech. I want to talk about an aspect, and a very peculiar aspect about graphene atomic thin layer sheets. And I want you, if you can elaborate about your research, what is the connection with your research? It's a peculiar fact that in the graphene atomic layer, thick graphene sheets, electrons behave like bosons. They behave more like massless particles. And I want to ask you, you talked about the Platonic solids and how they are incorporated in chemistry in this C60, for example, molecule. And my question is, if you now take this sheet of graphene and fold it in a Platonic structure, does it maintain this peculiar property of graphene?
No. Even if you make an nanotube,
no, it loses. Electrons start behaving again normally. So it's only if it's a 2D layer, single sheet of graphene that the electrons behaves like massless particles.
Even
very
more.
Peculiar. Yes.
Even more, if you take a 2D sheet of other material like molybdenum sulfide or tungsten sulfide, there is no such behavior. But we have with us Manos, who is in graphene, and also Kostas, I think. We work with only to try to see if the addition of graphene improves the stability of perovskite-based solar cells. But I know that both your guys, which I mentioned names, are now very active, and also the group of Aldo Di Carlo in Italy. We try to use graphene. And now there is another material which is called miscen, which for our purpose, for solar cell purpose, may be better than graphene. But this fantastic physics is only in graphene, as far as I know.
Okay. Thank you very much, Professor. Thank you very much.
Kostas, I would like to ask Professor.
Guys, okay, one more question, because I'm still in Heraklion. I have a flight from Hania, and I need to close this session.
One last question to Professor Katz. I would like to ask you if you know, are there any applications that we can say prefer this structure of the fullerenes, or they are studied till now? For example, the fullerene structure is preferable by some reactions, by some other materials to do what exactly? If you can ask, you can.
No, if you ask about applications of fullerenes, today it's not very massive. It's used in still research in medicine it's in inorganic photovoltaics. Carbon nanotubes now very rare, whatever. About inorganic structures like tungsten sulfide and molybdenum sulfide, they are very successful in if you talk about industry, in tribology, for mechanical application, big skills, it's very effective in tribology. But for research, it's also very, very interesting. They got a superconductivity, chiral superconductivity in this chiral Troop-Reshev is involved in this. Also some kind of photovoltaic effect without pin junction, just because of chirality of these big tubes. But I don't know if I would suggest you can take my email from Kostas, and I will also put my email in a PDF I will send to Kostas, and let's continue by email.
Okay, okay, of course. And from the scope of chemistry, I can tell you that chemistry prefers mostly the six structure, the six atoms, because of the aromaticity,
Sure.
the structure of benzene. But we prefer also, and the five the pentagons and whatever. Okay, it's not. Always the hexagons that are the abundant forms, we can have in other structures.
Sure, agree.
Yes, thank you.
So I think that we should close this session right now. We can see that, you know, symmetry and also the dimensions, they play an important role, because thanks to Manolis Markoulakis' question, we can see, like, you know, if we go from a single layer to multiple layers, you know, the properties are changing. So it's like symmetry and also the dimensions. That plays an important role on these physical and physical properties. I will say physics, that physics is everything. But from after Eugene Kant's talk, I think art is everything, because it seems that nature is like an art. It's not like physics or science, is an art. So thank you very much, Eugene. I will upload this recording on our YouTube channel of our International Relations Office. I would like to thank you again, Eugene, for this very nice talk. I think that, you know, regarding the number of questions and discussions that we have, it was a record. So this is also very important about the impact of the Sci-Cafe talks to the audience. I hope to have.
Kostas, now not only Manos is proud of himself, only now I'm also proud of myself.
I mean, we are proud of Manos, we are proud of your talk. We are proud that we are Greeks, because everything started from Archimedes. So everything is based to the movie of the Hollywood movie. I would like to thank you again. I would like to thank also the attendees and for their questions and for their participation. Until next Friday, I wish you to be safe and be well. And now Kalispera from Greece, because it's after 12. So bye-bye and thank you. Thank you, Eugene.
Thank you,
And
Eugene.
I'm looking forward to receive your PDF.
Yes.
Thank you. Bye.
Bye-bye.
Bye-bye.